Look who's early, just me. This is just for those recording people out there. Because no one's here right now. Put my feet up. Relax. Oh, Lauren, hello. And Camille is here? Oh, we had a video for a second. Well, it's just Lauren. It's just Lauren and Camille. Lauren and Camille show. That's fine with me. I think I've set the precedent of being about a minute late, but I'm actually early this time. Safa, welcome to the podcast.
Yo, what's up?
What's going on with you, man?
I've just been chilling like usual. What about you?
I've been chilling a little harder than usual. Wait. Or I guess I've been chilling softer than usual. What's it mean if I'm working harder than usual?
I guess you're working overtime. I don't know.
Working overtime, my friend. No. I'm trying to build this desk. I mean, look, we got a whole setup up here. Things are coming along, people. Things are coming along with the desk. I should be sending you guys updates on the desk situation. So far, we're still financially lucrative in the sense that it costs less for me to build this desk than it would have to buy it. But I'm thinking about tricking it out, and the tricks are gonna put me in the red, and that's no good. But I'm not a business major. I'm a math major, because that's all about having fun. Let's not worry about money, right? Let's just do math for fun. So welcome back, everybody, to Discrete Math. If you didn't already know the name. And start off, anybody have any questions, comments, concerns, things going on? I think I just fixed the quizzes so you guys can actually see your grade. I keep making it so grades don't go out, so you can't see your homework grades when we're only halfway done grading them. But then I remembered, no, wait, I need to fix that so you can see your quiz grades. So I have to go and do it manually. It's a whole thing. But I think I have it figured out. But if I don't, please email me and keep getting on me about that because it's embarrassing. It's frankly embarrassing. But anyway, any questions, comments, interesting things? Is anyone seeing discrete math in their daily life yet? Like you're seeing all the equations? Like you'll be talking to someone and they'll be like, yeah, you know, if basketball season happens, I'll go. And you'll be like, oh, that's an if then. That means if they don't go to the stadium, basketball season must have not happened. Huh? No one? No one's doing the contrapositive law in their daily life?
I mean, I'm a comp sci major, so I'm seeing Boolean algebra all the time.
There you go. Exactly. Yeah. I mean, for example, if you had an if statement, right? Like if you had, where's my advanced second camera? I think it might be better today because of the excess lighting in this room. Okay. If you had an if statement like if, let's say like not X and Y or something like that, that would be the same thing as if you had an if statement and you had not X or not Y. Right? Based on our De Morgan's law. It's already becoming useful. The point is, discrete math is where it's at, and that's where you're at. So let's do some more discrete math. Today is section 3.1, and here is interesting. I keep saying that this is a giant leap. This is going to be something new. That's because every class is another giant leap. So last time the giant leap we made is the idea of arguments. We introduced arguments, and arguments are the way that you go from the truth of premises to the truth of conclusions. And that's the whole thing about math, right? We have our whole web of like, you have truths down here, and you connect it to this truth and that statement. You connect all these statements. You do that through arguments. Here's the problem. And I'll write down section 2.3. Or 3.1, I mean. This is the whole thing. Here's the problem with that. So far, we cannot make implications about things that are not, or implications, meaning we also can't make arguments, I should say. Implications, arguments, all that, about things that are not definite statements. And here's what I mean by that. So far, we can say things like 2 is even implies 3 is odd, right? We can say that. This is totally fine. Makes sense. With current machinery, I'll say. However, we can't say that if x is even, then x plus 1 is odd. Why can't we say that?
Don't know what X is.
We don't know what x is. X is even is not a statement. Remember, and this works because we have statement implies statement, right? We can do statement implies statement, but x is even, this is not a statement. Not statement, not statement. However, this is really what we care about doing with if statements, right? With if statements in regular life, when we talk about math and things like that, what we really want to do is say, like, if x is any even number, then x plus 1 is going to be an odd number. It doesn't really help us to say that if 2 is even, then 3 is odd, because that would mean that okay, for every number, we have to have a different implication. If 4 is even, then 5 is odd. If 6 is even, 7 is odd. Capturing what's trying to be communicated here can't be done with this if then. And that's a big bummer, because this was great, because arguments, we could connect things, right? But something like this statement is a statement we really want to make. For example, I mean, you know, in calculus, like you have statements saying like the derivative, or let's say like if f is a power function, meaning like x squared, x cubed, whatever, or maybe I should say if f of x equals x to the n, then f prime of x is going to equal n x to the n minus 1, with the caveat of 1 over x, of course. But anyway, or to the 0, of course. But anyway, the point is, this isn't really an implication as we know it, right? Because is this a statement?
No, because we don't know what x is here either.
You know, actually, x is okay here, because f of x equaling x to the n, the x here just corresponds to things you plug into the function. The issue here is the n. We don't know what n is. Saying that f of x squared equals 2x, that's totally fine. We'll go over functions later. You guys have to know this. But this is just a function. So we're saying if we have this function, then its derivative will be this. But what we can't say is that for this general function where n is just some number, we get this, because what's n? This isn't a statement until we know what n is. It's a whole thing. Anyway, I was just using that calculus example to show you how it's important that we figure this out. And so the way we're going to figure it out is using something called predicates. So I'll say predicates, and they do relate to whatever the heck predicates mean in English class, but I became a mathematician for a reason. I forget what that means. But anyway, they are exactly what that is. And so let's do some examples. Does anyone remember what predicates mean in English? There's like indirect objects, direct objects, subjects. I don't know what it all means. Anyway, though, so we have predicates. Here's the example of a predicate. X is even. There's one. We also have, and hey, you know what? I'll label these so we have them for later. So I'll say example. We have, I'll call this P of X is equivalent to X is even. And then we can have Q of A, B, for example. That means A is B's parent. Or we could have the predicate R of Z, which means I have at least Z hats. And let's do one more, or do a couple more. We'll do S of C is equivalent to C drives a Kia Soul. And we'll do M of D is equivalent to D squared plus 2 equals 6. These are all predicates. And I haven't told you what a predicate is, but let's talk about this. What does, well, let's start over for a second. When I was saying that, like, the if X is even, then X plus 1 is odd thing, the problem with that, X is even, X plus 1 is odd, are in statements. And all of our logic works on statements. So the question really is, what we're trying to do is be able to turn X is even, X plus 1 is odd, kind of into a statement somehow. And so this is where we're going to start. That's our goal. Here's where we're going to start. How do these things relate to statements?
Are these like presumptions about statements that we can make? Or
Presumption.
like prerequisites, I guess, before we like define an argument?
I think I see a little bit of, I think I maybe understand what you're saying. But here's what I'm getting at. P of X, or this X is even, is not a statement, right? But what could we do to make this a statement?
Do we have to plug in something for X?
I literally have plugins in there for X on my notes here. Stop it. Exactly. We did not play this beforehand. Yes, predicates are sentences. What did I say exactly? Or I'll say a predicate wow, you think you could underline better. There we go. A predicate is a sentence that with finitely many variables that becomes a statement when we plug in subjects for the variables. That's the definition. And let's just look at these examples, see how it makes sense, right? X is even, that's not a statement, right? P of X on its own is not a statement. But if you plug anything into it, it becomes a statement. So for example, right? For example, P of 2 is equivalent to 2 is even. Is that a statement?
Yeah.
Yeah, 2 is a statement. It's true. 2 is even. A statement is just a sentence that's true or false. So no, so and we can do that one, right? Let's do Q of Brady Gronk, that's equivalent to saying, so you plug in Brady for A and Gronk for B, you get that Brady is Gronk's parent. Is that a statement?
Yeah.
Yeah. This one's false. No matter how much Brady acts like Gronk's dad, he's not his biological father, right? The point is that notice for all of these things right here, we can keep going, right? Like R of, someone name a number. How many hats do you think I have?
9.
R of 9 is saying I have at least 9 hats, which, if we count, let's see, oh, what's that? Like 1, 2, 3, 4, 5, 6, 7, 8. Oh, I have 9 exactly. So I do have at least 9 hats. Good job. So this is true. I don't know what it means.
Professor, I check our windows and make sure there's nobody there looking and counting.
It's a good point. I do keep my window open, so there's free discrete math lectures happening in my apartment. But anyway, so that's true. I have at least 9 hats. And we can go S of, let's say, a giant hamster. This is saying a giant hamster drives a Kia Soul, and that's true, based on those commercials from like 2009 or whatever. So the point is, all of these become statements when we plug in something. Does that make sense? I dropped a marker. I'll be back. And I'm back. So yeah, so all these things become a statement when you plug in something. I think that's nice and simple, right? I mean, these are basically kind of like logic functions, right? I mean, because if you have the function like f of x, if you have the function like f of x equals, I don't know, x cubed, right? X cubed is not a number, but if you plug anything to f, like you plug in 1 to f, you get 1 cubed, which equals 1, you get a number. So it's like a function, it's not a number until you plug something in. A predicate's not a statement until you plug something in. More of that arithmetic, logic, analogies going on here. Anyway, we good on this? Nice. Next. So that's what a predicate is. So now let's talk about the domain of a predicate. So just like how functions have domains, predicates also have domains. And what is the domain of a function? This is actually taught kind of wrong in some classes. I don't know why. So who's got me? What's the domain of a function? Like a normal function from, you know, algebra 2, trigonometry, calculus.
I guess to be honest, I don't really know how to describe it, but the best way I can is like kind of like the boundaries of like the x-axis.
That's not bad. I mean, domains, the way they make me feel is indescribable. But the actual definition of domain is just the things you plug into a function. That is it. And so sometimes, for example, like if you have f of x equals the square root of x, right? The domain is all real number x greater than or equal to 0. Why? Well, because if you plug something less than 0, you're taking the square root of a negative number, which doesn't really make sense if we're talking about real numbers. And so the domain is just a thing. It's just where you it's just the things you're allowed to plug into the function. And by allowed, I don't mean allowed by the universe. I just mean it's made up by people and made up so it makes sense. So I'll say the domain of predicates is exactly the same. It's domain of predicate is all possible values that may be plugged in, and I'll say defined along with predicate, and this ensures statements made from predicate makes sense. So all I'm saying here is that like P of X is a statement that is X is even, right? And this, I mean, it makes sense if you plug in a number. But what if I say that what I can plug into X, like what is P of Tim Sands? That means Tim Sands is even. He's even what? Like, what does that mean? It doesn't really mean anything, right? So you can see how you need a domain just to put some restrictions on what you can plug into X. It's just a restriction on what you can plug into X, and it's made up by us. So for example, so you can make it up. So P. So you could have P of X with domain in, where this in like this is the natural numbers. So 0, 1, 2, actually not 0, 1, 2, 3, 4, 5, 6, 7, those kind of numbers. You could have that, or you could say P of X with domain, I don't know, 1, 2, negative 7, 3, right? Right. The domain, you just define it along with the predicate to tell the person using it, to tell the reader what they're allowed to plug in, basically. And by allowed, of that, once again, that's not some magical law of the universe, right? That's just what we're defining it to be. And we're going to do some more examples of that right now. So that is domain. So for example, I'd probably do Q of AB with, it's interesting, Q of AB with domain pairs of humans, right? Because Q of AB, that takes in 2 inputs, right? So the domain, the things you can plug in are going to be pairs of things. And by the way, you can notice that the order is going to matter. We'll see that in a second. So yeah, that's domain. Any questions on that? Okay. Me holding a 5-second steely gaze means we're going to move on. And we are moving on to finally do something a little interesting with this kind of stuff. And this is, we're going to get very interesting in a second. And this is truth sets. So what's a good color for truth sets? Let's say pink. I like pink. So a truth set truth set. A truth set for a predicate, let's just call it P of X, with domain D. So you have a predicate, and D is just a collection of all things that or the collection of all things you're allowed to plug into P of X, is the set of all things in D that you can plug into P and get, or that you can plug into P and make a true statement. So it's everything you can plug into P and get a true statement, i.e. it's set of all X and D such that P of X is true. So that's all truth set. So we have this domain, and that's the things that you're allowed to plug into X, or plug into your predicate here. That doesn't mean that everything you plug into your predicate, everything in the domain is going to be true. The truth set specifically looking at the things that make it true. Good? If you guys know anything about functions, this is similar to the inverse map of a function. But anyway, the point is, yeah, since the truth set, let's do some examples. So for example, consider P of X with domain. So X is even with domain, we'll use Z. And Z is all integers, positive and negative. We'll go over these in detail later. So consider P of X with domain Z. Then truth set of P with domain D, that's going to equal the set of all X in the set of all X and D such that, I'm going to abbreviate such that with the ST, such that P of X is true, right? Well, in our case, that's just set of all X, and our domain here is Z. Oh, I'm sorry. I should have made this a Z. Right here, that's what I'm saying our domain is. I didn't define D to be that. Anyway, you get my point. There we go. So this is all X and Z, such that, what's it mean for P of X to be true? Well, P of X, that X is even. So this is just all X and Z such that X is even. I messed up the color scheme. But anyway, what this is this is what? So if we're looking at all the X and the integers that are even, well, you're looking at 0, 2, -2, 4, -4, 6, -6, on and on like that. And the little curly braces here, those are just used to indicate a collection of things, a set of things. So, does it make sense why this is the truth set of P? Because these are all of the things in the domain Z that you can plug into P and get true out. They're all of the integers that are even.
I have a quick question.
Hit me, yeah.
In order to define the truth set, do we need to know all the values that exist within it? Like if we're only using the predicate for like a certain thing that we know the predicate falls within, do we need to define the rest of it as well? Like everything else that could possibly be.
Oh, you're saying like this dot dot dot.
Right, yeah. Can we have a dot dot dot? Like if our predicate says that like x is even and it's a multiple of 3 and it's divisible by 24 plus it's a prime or something like that. Like
No, I see exactly what you're saying. So I put a dot 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 here because in this case it's obvious. We're gonna go over and for now you guys can kind of do this if it makes sense in the homework and stuff like that. But we're actually gonna go over more. We're actually gonna go over set notation later, and the way you write the set notation exactly is you say this is all things out of the form 2 times k, where k is itself an integer, and so that basically means this. So this is the precise way to write that. But for now, just let it be. Is that good? But you're totally right. You totally brought up a good point. Good. Good. Perfect. Cool. So that's the true set of P of X with domain Z. But we can have other domains. Remember, domains are just things we define them to be. So we could also consider P of X with domain D equal to 1, 3, 5, and 6. So now these are the only things that we're gonna set. We're gonna restrict the things you can plug into P of X to these, just cause. So now the truth set of P with domain D, that equals set of all X in D such that P of X equals true, which is set of all X in D is 1, 3, 5, 6. Such that X is even. Red and pink. Great color scheme, Daniel. Great way to tell us apart. Anyway, so what is this? What are all of the things in 1, 3, 5, 6 that are even, that you could plug into P of X and get true?
Six.
Just 6? Right, when they're finite, we can go through them. Like 1, okay, let's plug 1 to P of X. 1 is even, that's false, so it's not gonna be in the truth set. 3, plug it into P of X, 3 is even, that's also false, not gonna be in the truth set. 5 is even, also false on the truth set. 6 is even, hey, that's true. So 6 is the only thing we can plug into P and get a true value, so that's the only thing in the truth set. That's all this means. Any questions on this?
Do you think we'll work with more like limited truth sets like D is, or do you think we'll work with more like boundless ones like all integers?
Little column A, little column B, my friend.
A little bit of both. Okay.
No, shake it up. Yeah. No, it's gonna be cool. It's gonna be cool. Because I mean, one of the coolest things about math is infinity, right? I mean, so I would be doing you an injustice if I didn't show you any math. You know, that would be like having an MCU without Spider-Man. I love Spider-Man. Yeah. So I'll do one more example to show you something important, and that is consider Q of AB. So we're looking at this guy now, right? With domain D equal to all pairs of people in my immediate family. And so I'm an only child, so all pairs of people in my immediate family, that is me and my mom. There's me and my dad. There's my mom and my dad's another pair. Am I missing any? No? Yes? I don't know. I think someone might be thinking, crap, does order matter?
Would you switch it around so then it's mom and me and dad and me and then dad and mom?
Yes. Order matters, which is why we're actually going to end up defining these as ordered pairs. But order does matter. So this is mom and me, and then there's also dad and me. It's like a children's book. And there's dad and mom. All right. So order matters very much. Why does order matter? Well, let's think about plugging one of these pairs into Q, right? Q of me and mom saying I am my mom's parent, that's false. But Q of mom and me saying my mom is my parent, that's very true. So the order definitely matters. Gosh, I feel real comfortable clicking the kid-friendly blocks on YouTube this time when I put this video out. Yes, so order matters. Now let's look at truth set. Truth set of QAB with domain D. And so that's going to equal set of all. So now the things we plug in, things in our domain, they're not just an X, but they're actually a pair of things, A, B like that. So instead of all A and B and D, such that Q of AB is true, which is just the set of all A and B and D, such that QAB says A is B's parent. So, looking at, we'll make a nice big one here. Looking at D, right here, right? What thing's gonna plug in, which of these pairs is gonna plug into Q and get true out? Which one of these is the first entry, a parent of the second entry? Once again, it's finite, so we go one by one. Me and mom, plug that in. Am I my mom's parent?
No.
No, I'm not. So that's not going to be in. How about me and dad? Am I my dad's parent?
Nope.
Mom and dad's? Am I mom and my dad's parent?
Definitely not.
Throne. She's not.
Yeah.
No. Mom and me. Is my mom my parent?
Yeah.
Yeah. So mom and me goes in here. Mamma mia. And how about dad and me?
Yeah.
How about dad and mom? Once again, Game of Thrones, no. So, the truth set of Q of AB, so this predicate, with the domain, my immediate family, is going to be this. Now, if you use your immediate family, you know, you'd have pairs of sisters and parents and things like that. If you use a bigger family, you'd have aunts and like your aunt and your cousin or like whatever. Or if you had said D is all people in the world, you'd have to then put all pairs of people. You have to put Charlie Sheen and Martin, or Martin Sheen and Charlie Sheen. You have to put John Voight and Angelina Jolie. You have to put like Malik and Michelle Obama. All those things, right? So the point is, So the point is the domain just affects what we're looking at, just the scope of what we're looking at, and the predicate tells us this thing that will become a statement when we plug it in. Any question on truth sets? Good. Well, you can bet your life that you're going to see truth sets in your homework this next week coming up. But all right, we're moving on. 2. What's next? This is good. Oh, by the way, a truth set can be empty. I should mention that, right? So truth set of M of D with domain 3. Let's just say that, right? This equals set of all D, oops, you don't know that symbol yet, D and D such that M of D is true, which is set of all D in 3 in the set that just contains 3, such that M of D is 3 squared plus 2 equals, or sorry, D squared plus 2 equals 6. Is there anything in this set that you can plug into M and get true out? I mean, the only possibility is 3, right? Because it's the only thing in the set. And then you plug 3 in for M, you get 3 squared plus 2. That's 9 plus 2, which is 11, which is in 6. So this is just empty, which you write as that. So sometimes the true set's going to be empty. Sometimes not. All just depends. Any questions? I think that made sense. So, cool. I'm going to keep this right here. And now, let's talk about the big dog of this lecture. And that is oh, you can't see the big dog. There we go. And that is quantifiers. Ooh, quantifiers are nice. So here's the idea behind quantifiers. We've been talking this whole time about, we want to be able to take something like x is even, for example, right? And we want to be able to turn it into a statement. Because once we turn it into a statement, we can use all of our logic stuff on it, right? But the problem is, P of x, x is even, not a statement. One way to make it even, so I'll say, let's go green. Who knows why? For the health of the planet, Daniel. So one way to make P into a statement is to plug in a value. Right? So, example, P of 4 is equivalent to 4 is even, which is true, right? That's the whole thing about predicates. You plug it in and get a value. So we could do that, but we haven't really gained anything, right? This just feels like an extra step of saying 4 is even. P of 4 just feels like a more complicated way of saying 4 is even. But here's the key. There's another way to make P into a statement, and that is another way to make P into a statement is to say P is true for a range of values. Now this is a little interesting. So an example of this would be the statement for all, let's say, for all x multiples of 4, P of x is true. Is this a statement? Wait. They say for all x multiples of 4, we have P of x. This guy's statement, is it true or false? Does it have a truth value? Who thinks yes? It's a statement. Who thinks no? It's not quite a statement yet?
Yeah, it's a statement.
It's a statement, right? It's either true or false that all multiples of x will satisfy P of x. Or if x is multiple of 4, P of x is even, will be true. In this case, this whole statement is true. It is true that every multiple of 4 will be a will be even, right? It's only a statement. Yeah. Or you could say, there exists an x prime number such that P of x. Does it have a truth value? It doesn't matter if it's true or false. Just the question is, does the statement make sense? You know what I mean?
Yeah, it makes sense.
Yeah, it makes sense, right? This is a statement. So notice, this is actually really interesting. This, let me stop. This, the point is that, I got too excited to start going in a circle. The point is that right now we're just saying something, we just plug something in, we're just saying something about one number. Here we're saying something about all numbers, or we're saying that for all prime numbers, there's at least one. This is new. This is interesting. And what we're trying to do, and if we're trying to get to the point of saying, if x is even, then x plus 1 is even. If we're trying to get to the point of being able to make that statement and fold it into our logic, well, this is really saying that for any x, if x is even, x plus 1 is even. So you see how making stuff true about a range of values is really powerful. That's going to come up later. But anyway, for now, so the reason we call these quantifiers is because we kind of quantify on what ranges P of x is true. So here, what this statement is saying is that we're quantifying that on all, for the entire range of multiples of 4, P of x will be true. Here we're quantifying it, saying just for one, at least one of the prime numbers is true. So that's kind of the difference. And so this brings us to our two main quantifiers that we care about. And they have really cool symbols. And these will be the first really cool symbols you guys learn in math that'll make you feel really complicated, like you're in a movie, writing on a whiteboard or writing on a glass or a mirror, where they do in movies. And that is, we're gonna have, let's use colors. The universal quantifier over here, and we'll have the existential quantifier am I spelling existential right? Well, you can't even read what I'm writing, so it doesn't matter. Existential. Is it an S? When did I write this? It's a T.
It's a T. Yeah.
Yes, thank you. That's embarrassing. There we go. Existential quantifier over on this side. And I'll use purple to separate them because I know colors. There we go. So, the universal quantifier, this is, we give it a cool symbol. We give it this symbol right here, upside down A is the universal quantifier, and it means for all or for every or for any, things like that. It brings up the concept of saying that for whatever range we're talking about, our things got to work for all of them in there. And it's got to work for each one. Actually, that brings up another good point. We can also have for each. Yeah. So that's what universal quantifier is. So for example, if you had the statement, every Hemsworth brother is rich. I originally said handsome, but that's subjective. Rich is kind of more subjective, less subjective. Every Hemsworth brother is rich. Every, here you should be thinking for all. For all the Hemsworth brothers, they are rich. But how can we kind of put this more mathematically? We're saying every Hemsworth brother is rich. So what we're really saying is that for all people that happen to be Hemsworth brothers, they're rich. And so this right here, this is our domain. This is the domain of things we're talking about. Domain equals Hemsworth brothers. Which, if you don't know, are famous brothers, Chris, Liam, and Luke. No one knows Luke. He's I guess he's like moderately rich. And then is rich, this is like our predicate. We're gonna say P of X is rich. And so this statement can be rewritten as for all X and D, P of X. Saying for all people that are Hemsworth brothers, so all people in the set of Hemsworth brothers, they are rich. Does that make sense? Let's do another example. For each n of the natural numbers, n times pi is irrational. You don't even know what any of this means yet, but pi right 3.14, the decimal goes on forever, it's irrational. The question is n pi, like 1 times pi, 2 times pi, 3 times pi, 4 times pi, is that also going to be irrational? But we don't really care what it means right now. We're talking about, can we rewrite it? And notice that this above statement is, I'm going to call it true. All the Hemsworth brothers are rich. The point is, this is a statement, has a truth value. Wait, back down to here. So for each n of the natural numbers, n pi is irrational. Let's check this out. So for each n and n, well, this is clearly our domain, right? That's D. N pi is irrational. That's what we're saying about each n and n. the statement we're making is that imp I is irrational. So this is kind of our predicate. So you could call this like Q of n, something like that. And then this for each, that quantifies how many things in the domain we're talking about, and that's all of it, the for all. So the way you can rewrite this is that for all n and d, Q of n. Does that make sense how this is related to this? Doing all right? We'll have a bunch of examples, so don't worry about it too much. Now let's go on to existential quantifier. So the definition here is that the backwards E is the existential quantifier. Am I gonna go off? I'm gonna go off. Yeah, is the existential quantifier like that? And it means there exists, or there exists, whatever it is. There exists, or there is some, or for some, something like that. So for all, what for all means is that whatever you're talking about works for everything in the domain. Kind of the opposite of it working for everything in the domain is it working for at least one, right? The opposite of everything is just kind of one, you know, if that makes any sense. And we're gonna see it, these statements, the for all and there exists are kind of yin, they're kind of like a yin yang situation going on. But anyway, that's what there exists means. So for example, if you had, there is some pair of people in this Zoom with the same birthday, that's a statement, right? And what's it saying? It's saying, well, it's saying there is some. So it's saying that there exists, there's some pair of people. So it's saying there exists a pair, right? We'll call it AB. In, actually, I'll go XY, just to show you can do whatever you want. In XY, in this Zoom, that's like your domain. Your domain is in the domain is pairs of people in this Zoom. Pairs of people in this Zoom with the same birthday. So what are we saying about these pairs of people in Zoom? We're saying about at least this one person, this one pair of people in the Zoom. We're saying that X and Y have the same birthday. And we can call this, oh no, let's call it RXY. So RXY is that X and Y have the same birthday. And so how can we write this sentence in our more math notation where we say, well, there exists a pair in the pairs of people in Zoom such that RXY is true. So they have the same birthday.
I've got a quick question.
Yeah.
Is there any like notation or verbiage for when the order of the pairs or the variables don't matter? Because previously we said like if we have a pair, sometimes they do matter, and then in this case it doesn't. Is there like some notational difference between those two?
Yes.
Or is that like out of the scope of this class?
That's a little out of scope of this class.
Okay.
Talk to me after class. I'll tell you the difference there. For now, just assume everything in this class is as the pairs ordered. But anyways, it makes sense how this statement's the same thing as this statement right here. And by the way, is it true? Wait. Let's go through real quick. My birthday's June 22nd. Anybody match with that? Camille, what's your birthday?
January 7th.
January 7th. Anybody match with January 7th? What else we got here? We got November 20th. Anybody match with that? May 26th? July 11th. September 30th. Oh, it's coming up. December 31st. December 28th. Oh, dang, close. No? Okay. Well, that's okay. Doesn't matter if the statement's true or false. It just matters that the statement is going to be one of the two. And in this case, it happens to be false. We were close, though. So that's an essential quantifier. I'll do one more example with this, and then we'll get out of here. So, an existential, another example of existential statement would be there is a power of 3 such that it is prime. I'm sorry, no. Such that it is even. Actually, I'll say prime. And prime number we'll define later. That just means it's only divisible by itself in 1. So there's the power of 3 such that it is prime. But once again, this there is, we should be thinking there exists. Or maybe I should say to you a little more practice, a little less obvious. For some power of 3, I'll say some power of 3 is prime. Let's just start over. Some power of 3 is prime. All right. Why is that interesting? Because, or how do we translate this with the there exists symbol? Well, some power of 3. The power of 3 here, powers of 3 are going to be our domain. We're saying something about the powers of 3. And these powers of 3, they're 1, 3, 3 squared is 9, 3 cubed is 27, 3 to the 4th is 81, on and on like that. So we're saying something about the powers of 3. What are we saying with powers 3? Well, we're saying that there exists, well, at least one power of 3, such that it is prime. So here, kind of our, I don't know, let's just call it m of A is equal to saying A is prime. So we can rewrite this statement. This whole statement is equivalent to there exists an A and D such that M of A, such that A is prime. That's all we're saying. This is an existential statement, and this over here is a universal statement. A universal statement, you know, they both say something about a domain, right? So they say something about a domain. The thing they're saying is the predicate, and the quantifier tells you exactly the range of the domain you're talking about. For all saying for all the things in the domain the predicate's true, there exists is saying for at least one thing in the domain the predicate's true. But we'll do that next time. Any questions?
Could you scooch the board over a little bit to the left?
What do you say?
Could you scooch the board a little bit over?
Oh,
to
I'm
the-
so sorry
to
about
the
that.
right side. Yeah, there we go.
There you go. Yeah. So we're saying for some power of 3 is prime. That's saying there exists a power of 3. So there exists something in the powers of 3. So 1, 3, 9, 27, 81, on like that, such that it is in fact prime. And is this true?
No,
No.
it can't be true
Why can't it be true?
because
we haven't defined prime yet, but once we do, we know that
Power
have
of-
a multiple of 3.
yeah, power of 3 implies it's not prime.
What about
Uh,
3 itself?
that's
Uh,
cheating.
That's cheating. It's a power of 3. It's 3 to the 1.
is one power of prime?
So you know, so it depends on how you define power of 3 and all that. But we're defining power of 3 to include 3. Then it is going to be true because 3 is prime. Once again, don't worry if you don't know what a Hemsworth brother is. Don't worry if you don't know what a rational means. Don't worry if you don't know what primes are. Right? The point isn't any of the specifics. The point isn't if it's true or false. The point is that it is going to have a truth value. So we just made, right? We just figured out a way to make this predicate, right? M is a predicate. Q is a predicate. We figured out how to make these predicates into statements by defining a domain on which we're saying something about them, right? That's freaking brilliant. And that is how we connect. That's how we connect these predicates, these kind of open-ended things, to real statements. And then we can actually start to do like the if x is even, x plus 1 is odd thing. And that, boom, math. Math comes from there with some more key steps in between. But anyway, if no one has more questions, I'll stop recording. It's been a good week, everybody.